Welcome to the lecture An Introduction to Large Deviations, and today I would like to continue discussing the definition of large deviations and also talk about large deviations for the empirical means for independent random variables. Actually, we will consider the Kramer theorem, and from the Kramer theorem, we will try to obtain the large deviation principle according to the definition which we formulated last time, and I will recall in a few seconds. Definition. Let's recall the definition of large deviations. It is definition 3.1 in the lecture notes. And we say that a family psi epsilon of random variables in some metric space E satisfies the large deviation principle and shortly we will write LDP in, as I said, the rate in the metric space E with rate function I, that is a function from the metric space E to 0 infinity. If for any Borel set, any Borel measurable set A from the Borel sigma algebra, one has that minus infimum x belong to the interior of the set A is less or equal than lower limit epsilon goes to 0 epsilon logarithm the probability psi epsilon belongs to A. Of course, this is less or equal than upper limit by the properties of lower and upper limits. Logarithm psi epsilon belongs to A. And this has to be less or equal than minus infimum I of x. X belongs to A closure. And also we said that we also formulate the large deviation principle for the family of random variables in the metric space. Just remark that a family or a countable family psi n satisfies the large deviation principle also in the metric space E with rate function I if, and here we actually has to repeat or almost repeat the definition only with the change that n goes to infinity, and here you put that speed of convergence. So an now, an it is some fixed sequence which goes to 0, logarithm probability psi n belongs to A and is less or equal than limit n goes to plus infinity an logarithm the probability psi n belongs to A and less or equal than minus infimum also over x belongs to, but now a closure, the function x of I, where I is called the rate function. And as an example of a sequence which satisfies the large deviations, last time we discussed example. For instance, if we take psi n, which has normal distribution with covariance that is an identity matrix, and psi n are vectors, d-dimensional vectors, and independent, then last time we said that 1 over n Sn, where Sn it is the partial sums of psi n, satisfies the large deviation principle in Rd with the rate function I of x that is equal to norm of x squared divided by 2, and the sequence an it is 1 over n. And also, moreover, last time we noted that considering the family of square root epsilon, say psi1, or just psi, where psi has a standard normal distribution, as psi n, then this family satisfies also the large deviation principle in Rd with the same rate. Divided by 2, but now according to the definition which is written here. And today I want to talk about an equivalent formulation of large deviations, which is quite useful to work with, and also about further examples for a large deviation principle. Let me start with the following lemma. It is important lemma, and it is important to remember that that result, since that result is used often. And sometimes it is considered as a new formulation, as another formulation of definition of large deviation. A family psi epsilon satisfies the large deviation principle in a metric space E with rate function I, if and only if, shortly we will write if, it is if and only if, one has that upper limit epsilon goes to 0, epsilon logarithm, the probability psi epsilon belongs to f is less or equal than minus infimum I of x, x belongs to f, for every f closed, and second, the lower limit epsilon goes to 0, epsilon logarithm, the probability psi epsilon belongs to g is larger or equal than minus infimum I of x, x belongs to g, but now for every g open. So therefore, once again, to get the large deviation principle, one doesn't need to consider any Borel measurable set and show the inequality as here. but it is enough to consider only closed sets and check the upper bound, and then consider open sets and consider the lower bound. And as I already said, this statement here often is considered also as a definition in the literature, since most formulations are equivalent according to the statement of the lemma. And let me quickly discuss the proof of the lemma. The proof is indeed, I would say, very simple proof. First of all, let's note that these two inequalities in the lecture notes, they are denoted by numbers 3.3, and let me follow that notation here, and that is 3.4. Then we remark that 3.3 and 3.4 immediately follow from the definition of large deviation principle. For instance, indeed, let's check only 3.3. Take F that is closed set. Then, according to the definition, I will take the upper bound only. Epsilon goes to 0. Epsilon logarithm the probability that psi epsilon belongs to F. It's less or equal than minus infimum, and here you need to take infimum over F closure. But F is closed, therefore F closure, it is F, since F is closed. And this implies 3.3. And the same proof for 3.4 for the lower limit, since the interior of open set is the same open set that gives you that inequality. Now we will check the inequality, that statement in another direction. We assume that both inequalities here are true. Then in this in that case, just for an arbitrary set A that is Borel measurable on the metric space E, we have that minus infimum x belongs to A interior, I of x is less or equal, and this set here, it is open set. Then we can, therefore, we can use here 3.4 inequality, the lower limit for open sets, and obtain the lower limit, epsilon goes to 0, epsilon logarithm, the probability that psi epsilon belongs to A interior. But also you know that A interior is a subset of A. Then we can continue as using the usual the monotonicity property for probability. You get epsilon goes to 0, epsilon logarithm the probability that psi epsilon belongs to A. And then you can continue because the lower limit is less or limit infimum is less or equal than limit supremum. And you will have epsilon goes to 0, but sup. The probability that, so here, I'm sorry, here has to be epsilon logarithm probability that psi epsilon belongs to A. Then you can continue, just consider, replace A by A closure that contains A. And then you use the upper limit for closed sets. That is the inequality 3.3. And it trivially gives you epsilon logarithm. Oops, I'm sorry. It has to be a minus infimum. X belongs to a closure, because a closure is the closed set I of X. That implies the proof of the statement. Also, I would like to note remark 3.3 that a similar statement to this lemma can be done for a countable family of random elements. Can be, say, proved for a countable family of random variables in E. Of course, I will not formulate, but I hope you understand that I mean that here you will have a limit, you will have an, then logarithm, here xi n, here n goes to infinity, will be less or equal than that infimum for f closed, and the same for open sets. We will not focus on that. Now, one of the convenient statements, or let's say that differently. You see that to check the large deviation principle, either you need to consider an arbitrary Borel measurable set and then show the bound from below and from above, or you can consider open sets and closed sets and prove the inequalities for that set. But when you want to but when you have some example of random variables and you want to check whether they satisfy the large deviation principle, it can be complicated to consider an arbitrary, say, open set and prove the inequality for open sets, and the same for closed sets. So therefore, we would like to have some statement which would help us or allow us check the lower or upper limits for arbitrary sets, like in the statement, but checking a little bit less than we need. And my next the next proposition, it will be about the lower limit. It turns out that lower limit, it is some kind of local property that you need to consider what happens locally for every ball, and if that property which we will formulate happen, that immediately you will get the bound from below. For the bound from above, you can also get the statement which allows to check less, but this case we will discuss in our other lectures. Now I would like to focus on the limit from below, because in that case you don't need to develop the theory of large deviations much to get that and to prove that result. Let me formulate that proposition. 3.5. And here, let's assume, as before, we are on the metric space. We have the rate function I. And now, let's assume that let there exist a set E0 that is a subset of the metric space E. There exists a subset E0 such that two properties are satisfied. First of all, for every point of this, say, good set or set of points with some kind of good properties, we have that for each x from E0, we have that limit epsilon goes to 0, the lower limit, epsilon logarithm the probability psi epsilon belongs, but now we consider only the case when psi epsilon belongs to the ball with the center at x and radius r, and it is larger or equal, and then according to the definition of large deviations, you need to write the infimum over the ball. But here we want to do something else. We want to also send radius to 0 and consider that limit, that double limit, and and this has to be larger or equal than minus rate function I of x, when Brx is the ball in or with center x and radius. And the second, this set E0 is large enough. That means that for every x, let's write that by words, for each x satisfied that the rate function is finite. We don't need to go through all x, only for x that rate function is finite. There exists a sequence of points xn from E0 such that xn approximate x in the metric space E, and the rate function of xn goes to the rate function of ix as n goes to infinity. And when these two conditions are satisfied, when you can build some smaller sets E0 of points for which you have this inequality, and this set is large enough in this sense, then the lower bound holds. So you have the lower bound for every open set. Then lim epsilon goes to 0, epsilon logarithm the probability psi epsilon belongs to an open set G is larger or equal than minus infimum I of x over G for every G open. Oh, you see that we need somehow check locally what happens with the random variable psi epsilon, and this leads us to the lower bound. Later, we will use that proposition often to prove the lower bounds for some concrete examples of sequences of random variables. Now I want to prove the proposition. Here we only need the definition, use the definition of large deviations and also some analysis. And first of all, I want to note that this inequality trivially follows when the infimum is finite. If infimum is no, I'm sorry, once again. That inequality holds always in the case when infimum is equal to infinity, because minus infimum, it is minus infinity, and of course the inequality is satisfied. Therefore, we have to focus or we have to be focused on the case when this infimum is a finite number. And without loss of generality, assume that infimum G is a fixed open set, is fine. And then you know that according to the definition of infimum, we have the following. Let delta larger 0 be an arbitrary positive number. Be arbitrary. Be an number. Then you have that then they exist x0 from G such that I of x0 is less than infimum I of x belongs to G plus delta. Once again, it makes sense to draw some picture. For instance, for different x, you have the values of I of x, which are somewhere here. Then the infimum, it is that number. So it is like the maximal lower bound. And then you see that if we make step according to the definition of the maximal lower bound, when we make that step epsilon, then always, and that point is infimum of I over G, then this point is, so here you have infimum I over G plus delta, then you can see that there exist some points, or at least one point, such that the value, so that green point, is smaller than infimum plus delta. And now, by 2, you see that the set that we choose is 0. It is large enough that you can approximate if the rate function is a finite number, then you can, and now it is. So for that x0, that is a finite number because this is a finite number. You can approximate that x by the points from E0 by such a way that also the rate functions are close to each other. Therefore, in that case, so we claim, or by 2, and the fact that G is open, and the fact that G is open, we have that we can find some, say, x tilde from G intersected E0 such that I of x0 is close enough to I of x0. But for me, it is enough to write like that. So that it is not larger than I x0 plus some delta. Of course, here you can say more, you can say even absolute value is less than delta, but for us it is enough only this inequality. Once again, the fact that xn goes to x and that the set G is open allows me to claim that that points, which gives me the closeness of rate functions, will belong to E0 according to property 2, and also to G, because the limiting point belongs to G and G is an open set. And now let's also note that for that point x tilde that is from E0, we have the first inequality. We can use that inequality. And you see if that according to that limit, you can claim that if R is small enough, that this object will be larger than that result minus some delta. Let me write that. And by 1 and the openness of G. Once again, here the picture, you have the set G. You have x tilde, that is the point in G, and also it belongs to E0. And the openness of that, we have that there exists a radius that is small enough such that the ball of radius r with x tilde will be in G. It is because the radius, you can take radius smaller and smaller. G is an open set, and then you will have that ball br x tilde is completely in the set E. But since the radius of ball goes to 0 and x tilde is an element of E0, you have that inequality. Therefore, you obtain limit epsilon goes to 0, epsilon logarithm the probability psi epsilon belongs to b r of x tilde is larger or equal than minus I of s minus some delta. And now we can put that all inequalities which we wrote here together and get the limit from the bound from below. Consequently, we obtain that the limit epsilon goes to 0, epsilon logarithm the probability that psi epsilon belongs to G. First of all, we use that for this radius R, ball is a subset of G, and then by the monotonicity of probability, we have that probability is larger or equal, that limit is larger or equal than the limit epsilon goes to 0, epsilon logarithm the probability psi epsilon belongs to the ball. But now this probability, according to that, is larger or equal than minus I of x. I'm sorry, I forgot here to put tilde, right? Because in this inequality, you see that here you have x and here you have the same x. Then here you have tilde minus delta. Now you see that you have that I is larger or equal than I of x0 plus delta, but when you have minus, then you need to invert that inequality. And then you have minus here and you have minus there. And let's use that inequality and replace I by minus I of x minus delta and minus the delta which is left. Together it's 2 delta. I'm sorry, it has to be x0. It is x0. But we have chosen this x0 by such a way that we have that inequality. And again, when you put here minus, you invert the inequality here, you have minus here, and you have minus here. Then you can continue your estimate, replacing by the rate function at x0 by the infimum, but you will have one additional delta. Larger than minus infimum, x belongs to G, I of x, larger. You already had 2 deltas, but now you will have 3 deltas. And you see that the left-hand side, it doesn't have delta, and your delta was an arbitrary positive number, for which you obtained that inequality. Then you can make delta going to 0. Let's letting delta going to 0. We get the I'm sorry, the lower. This ends the proof of the proposition. Let me also note that the same statement is true in the case of sequence of countable family of random elements. Also, similarly, only one can a similar result for a countable family of random variables psi. And this proposition, in particular, also for countable family of random elements or variables, we will use later. And the statement is indeed very convenient because you see that now having that statement, you don't need to care how to prove the inequality for every open set, but you can just focus on the proof of inequality or a kind of inequality only for both. That, of course, it's easier with. Good. Now I want to prove the large deviation principle for empirical means. For empirical means, we have proved the Kramer theorem, which gives you that the lower and upper bound of the lower and upper limits, just considering the sets, or considering that the case that the empirical mean is larger than x or smaller than x and so on. But now we would like to get the statement or the bounds for an arbitrary Borel measurable set and understand what is the right function in that case. And we will start a new short topic in the lecture note, large deviation principle for empirical means. Empirical. And 4.1 LDP for empirical means in 1D in dimension, or maybe it's better to write in R1 in R. And as before, we will consider that we have a family of independent, identically distributed random variables, and let's formulate that as a statement, proposition 4.1. Let psi1, psi2, and so on be independent, identically distributed random variables in R, one-dimensional case, with mean mu, that is a finite number, and cumulant generating function phi of x, that is, I'm sorry, phi of lambda, that is a logarithm of the expectation e to the power lambda psi 1. Let also Sn be the sum of random variables xi1 to xin. Then we have that then the family one over n Sn satisfies the large deviation principle in R with the rate function I of x that is phi star of x. That is the Fenhill-Legendre transform. It is supremum lambda over R lambda x minus phi. That is x. Okay. Now we want to prove that proposition. And for the proof here, we will use the Kramer theorem. We already showed that, let's write proof. And that note that according to the Kramer theorem, we have, so on one has, that the probability that the limit and at n goes to infinity, 1 over n logarithm the probability that 1 over n Sn is larger or equal than x is equal to minus phi star of x for x larger or equal than mu, and also limit n goes to infinity 1 over n logarithm the probability that 1 over n Sn is smaller or equal than x is also minus phi star of x for x less or equal than mu. By the way, I forgot to say here that in the formulation here, if we work with a countable family, then according to the definition of large deviations, we also need to say what is an here. An is equal to 1 over. Okay, let's go back to the proof. We have this result, and now having that result, we want to obtain the lower and bound and upper limits like in the definition of large deviation. But here we will use the lemma, which says that we need only to show the bounds for closed sets and open sets. Then let me start with the case when the set is closed. We will use this lemma. It is lemma which has number 3.2. First, we will use that lemma. We will start in that from that case. First, we will consider F open, and we will show that bound. But here we will write 1 over n, and here we will have 1 over n as n. And here this function I, it is phi star of x. .2. Okay, let F subset of R be closed. First of all, let's assume that F is a subset of the interval from mu to plus infinity, where mu is the expectation, and we separate that case that f is or all points of f are larger than mu, and also then all points of f are smaller than mu, and then we consider the case when both can happen, because you see that here we have two different statements, and then we want to also, we must separate that cases to be able to separately use that property or that property. Let's start from that, and then we know already that the function, that the Fenkel-Legendre transform is, or phi star in this case, is a convex and increasing function. Since phi star is convex and increasing on subinterval from mu to plus infinity, it was an exercise in the lecture notes, and I do not remember, probably also you got that exercise as an homework exercise. It is easy to see. It is indeed easy to see, that infimum of x belongs to f of the function phi star is equal to phi star of x0, where this x0, it is a minimal point of f. You have some set f, your function is decreasing, so therefore you get the minimum in the left point of the set f. But the set f is closed, therefore this endpoint, it must belong to the set f, which we denote also by x0. And then we can estimate let me here draw also the picture. Here is mu. You had the set f. That point here, it is x0. Oh, therefore, you have that limit n goes to infinity, the upper limit, 1 over n logarithm, the probability of 1 over n as n belongs to f is less or equal, and then you can estimate that limit by the limit that 1 over n as n is belong to this complete interval from x0 to plus infinity, that we can write as the empirical mean is larger or equal than x0. And for that, you have the Kramer's theorem, which tells that it is minus phi star of x0. But by the choice of x0, it is infinite. And also similarly, we can get the same bound for the case if we get the same result if f is a subset from of all points are smaller or equal than. And now it is 2 and now 3. If f is not subset of I mean, it is not subset of f mu plus infinity, and also f is not subset of minus infinity mu, then we can consider only the part of f, the part of points that are smaller than mu, and all points of f that are larger than mu. Let me denote that consider. F1, that is f intersect with mu plus infinity, and f2 that is equal to f intersect with minus infinity comma mu. That of course are not open, are not empty sets by the assumption, and union gives the set f, and also f1 union f2, it is the set f. And for these two sets, we can get the following estimates. Limit 1 over n, the probability that logarithm, I'm sorry, I write something stupid, that logarithm, the probability 1 over n as n belongs to f is less or equal than the limit. And now you can use the subadditivity of the probability measure to get the estimate, because f is the union of two measures. You have that the probability that that random variable belongs to f is less or equal than sum of probabilities that this random variable belongs to f1 or belongs to f2. Logarithm, and here you have the probability 1 over n as n belongs to f1 plus the probability that 1 over n as n belongs to f2. And now, as an homework exercise, you had to show, it was exercise in lecture notes 3.8, but also you got that exercise for homework that say that let you have two sequences, an and bn. Be positive real numbers. And you then one can show that the upper limit n goes to infinity, 1 over n logarithm an plus bn is equal to the upper limit 1 over n logarithm an maximum this, we write that for maximum limit n goes to infinity 1 over n logarithm b. And now you see we have a sequence of positive numbers or no, negative numbers, and then according to that exercise you get that this limit is equal to the limit of to that limit when you consider only the logarithm of first probability, and then maximum with limit, and then you consider logarithm of the second probability. Then that is equal to limit 1 over n logarithm the probability 1 over n as n belongs to f1 plus, oh, I'm sorry, maximum of limit 1 over n logarithm of the probability 1 over n as n belongs to f2. And we have shown that that for f, let's know that this f1 is a subset of this interval, and for that interval, for that case, we have obtained that the limit can be estimated by minus infimum, but infimum is taken over the set which is here. that is minus infimum, x belongs to f1, and then phi star of x, maximum, and then you have minus the same for the second. Of course, when you put that minus outside, you will have minus, and then it is infimum over f1 phi star, but now you will have minimum infimum f2 phi star. And it is the infimum over f, over the union. That proves the upper bound. Now we need to work a little bit more harder to obtain the lower bound for open sets. But for that, we already have a statement which says that it is enough only to check the inequality for balls that in one-dimensional case are intervals. We next continue with a proof of lower limit, and for that we will use the proposition which we proved where we check the inequality only for balls. We next prove then lower limit. Oh, the lower bound, I'm sorry. That tells that limit n goes to infinity, 1 over n logarithm, the probability 1 over n Sn belongs to G is larger or equal than minus infimum x belongs to G I of x for every G that is subset of R is open. And for that, we need to, we will use the proposition which was formulated, which was obtained here. Actually, we consider the set E0 a subset of E, for which we can prove that type of inequality. We consider the ball, we consider as before the lower limit, but after that we also send radius to 0, and we want to see that the result is larger or equal than minus the rate function. In our case, it has to be minus phi star. And also this set is large enough in the sense that all point x for which the rate function is finite, you need to good approximate. Now for our proof, we take E0 that is equal to x from R such that phi star of x is finite. And since E0 has to good approximate all points for which that the rate function is finite, then of course that second property is automatically satisfied because actually we took all points for which the rate function is finite. In this case, the property here from proposition 3.5 is satisfied. The property 2, I'm sorry, from proposition is satisfied. And now we fix, x0 from x from E0 and such that x is larger than mu. Okay, it is the first case. We consider x from x0 that is, and as I said, our goal is to prove, consider a radius going to 0 and then limit of here are positive and goes to 0 as radius. And then 1 over n logarithm the probability 1 over n Sn belongs to the ball, but the ball with center r and radius with center at point x and radius r, it is the interval. It is x minus r, x plus r. And we want to see that this is larger or equal than minus phi star of x. It is what we want to. And now, since we considered the case x that is larger than mu, here is mu, here is x. Let's take r such that the point x minus r divided by 2 is larger than mu. And so we take r larger than 0 such that x minus r divided by 2 is larger or equal than mu, and note that phi star at the point x minus r divided by 2 is less than phi star of x plus r. Because you remember that the function phi, it is increasing function, and also there was an exercise or you can consider that as an exercise that phi star is strictly increasing function. Therefore, when you consider the value at this point and also the value at the point x plus r, two values will be different and one will be smaller than another. We will need then just to make easy computations in the next line. And then choosing that r, you see that when we take limit, then n goes to infinity, 1 over n logarithm, the probability that 1 over n Sn belongs to x minus r and x plus r is larger or equal than limit, and then n goes to infinity, and then you just take first of all the smaller interval, that is x minus r divided by 2, x plus r. Here maybe the picture once again. We had mu, it was r, it was x, it was maybe let's also take r such that also here you have freedom of choose r as small as possible, that is minus r divided by 2, just to be sure that also x minus r also is also is larger than mu. So therefore you have your intervals that you want to work. It is here x minus r, here is x plus r. And now you want to replace, here the idea is that I want to put here the closed bound, because the probability that I have here, logarithm, the probability, I want to write as a difference of probabilities for which I know what the limit is. It is limit n goes to infinity, 1 over n logarithm, and here I have the probability, and then I have the difference that 1 over n Sn is larger or equal than x0 minus r divided by 2. That is the probability that your random variables is here minus the probability that it is there. Minus the probability that 1 over n Sn larger or equal than x0 minus r. And then here, since we care about that the worst rate or the worst rate of convergence of exponential convergence, actually here the result, it should be the result which is which so here the result should be obtained from the probability which has like the worst rate of convergence. Then also I will need some exercise which also you will get. You can use the analysis to prove that. It is exercise. In lecture notes, it is 4.2. You can see there the precise formulation, which also I will try to formulate here. AN is, you have a sequence of numbers, but now AN is strictly larger than BN. B positive, B positive, and real numbers, such that there exist limits which are equal to A, it is 1 over n logarithm AN, and also B, it is a limit goes to infinity 1 over n logarithm Bn, then or show that the limit 1 over n logarithm of an minus bn, actually it gives nothing. So this bn is gives nothing to the result because b has the smaller rate of convergence. Here I forgot to write s, and a is smaller than b. And it is one of the assumptions. So then show that. So if this limit is smaller than that limit, then actually that result, it is exactly A. Is the result what is without B. And the same here. Now you have that this converges to phi star it's converged to minus z1, and this converge to minus z1. So therefore, using the property which the exercise that we obtained, you will have minus phi star of x0 minus r divided by 2. So here you obtain it larger. I'm sorry. Here should be, of course, B. So because we have that inequality, then of course we just say that also additionally assume that limits are not the same, that the A is strictly larger than B. But now you remember that when we talk about the convergence of that object, we will obtain minus of that one. So therefore, with minus, you will have here inequality minus. So then it is your A and this is your B in the exercise. And therefore your result, it will be A. Oops. Good. And then everything what we need to use, just you see that here we started from the limit, we obtained that one, and then let's make r going to 0 and use also the continuity plus continuity. T implies imply. Let me denote that by. Let me denote that by. It was in the lecture note 1.4. Then it implies 1 point. Let's finish the proof of the statement about the large deviation principle for the empirical method. Unfortunately, I'm a little bit out of the time, but I don't want to come back to this question next time. And let me just formulate a little, just shortly formulate the statement without the proof. That is the generalization of the result that we obtained, and to the multidimensional case. It is multidimensional. Kramer's theorem. Or it is also like large deviation principle for empirical mean in R&D. And also, as before, we defined now for a random variable psi in R&D, we define the cumulant generating function as before. It is phi, say xi of lambda or phi of lambda. It is logarithm expectation e lambda, but now you consider dot product or inner product lambda with psi. Well, this dot, it means lambda 1 xi1 plus and so on plus lambda d xi. And also we can define the Fenhill-Legendre transform. As before, it is supreme, but now lambda belongs to Rd. Lambda dot x minus phi c of lambda. Oh, I'm sorry, it is x. Is the Fenhill is the Fenhill-Legendre transform. Then the following theorem called theorem 4.5 due to Kramer, which says that let psi1, psi2, and so on be independent, IID, independent identically distributed random vectors or random variables in D with cumulant generating function phi x with, let me write just by words, cumulant function phi, and that Sn will be as before, psi1 plus and so on plus psi n. Then if phi is finite in a neighborhood of 0, of 0, then the family 1 over n Sn satisfies the large deviation principle in Rd with rate function I of x that is phi star, that is the Fenhill-Legendre transform, and the sequence an is equal to 1 over n in the definition. I don't want to repeat the definition of or inequalities in the definition of large deviations. we will have we will not prove the theorem since we will need to spend some time for that. But now I showed you some idea how everything works in one-dimensional case. Therefore, if you want to know more and go deeply into this type of questions about large deviations for empirical mean, in lecture notes, you can find some literature which I recommended where you can read or where you can find the proof of large deviation principle. In this case that was formulated here in the statement, and also in different literature, you can also find different types of proofs depending on assumptions. In some literature, you can find the proof that is easier when, for instance, phi is finite everywhere. In other literature, you can find the proof of the statement that was formulated here that I assume that is like more general. Okay, then it is everything for today. And next time we will talk about the uniqueness of the rate function for large deviation principle. We will talk about the lower semi-continuity of the rate function and also about the goodness of. Next time we will focus our discussion more on some properties of rate function, on the questions of uniqueness, and so on. And it is everything for today. Thank you so much for your attention.